In modern data science, datasets often contain hundreds or even thousands of columns, which we call features. You can see this represented by this large data table on the left. Now, feeding all 500 of these features directly into an AI model creates a massive problem. It makes the training process incredibly slow and computationally expensive. But worse than the cost, it often results in poor performance because much of that extra data is just redundant noise that confuses the model we are trying to train. This is where principal component analysis, or PCA, comes to the rescue. PCA is a mathematical technique designed to compress these hundreds of features into a much smaller, manageable number, say just 10 features, while retaining the most critical information from the original dataset. If you want to understand PCA without getting bogged down in the math, think of it like a professional photographer visiting the Taj Mahal. The monument is a massive, complex, three-dimensional structure, but a photographer has to capture it in a flat two-dimensional photograph. If they stand right in front and take the photo from this front view, they capture the beautiful dome, the tall minarets, and the reflection pool all at once. This specific angle provides the maximum amount of structural information possible in a single flat image. It tells the best story. On the other hand, if they took a photo from directly above, or perhaps from a strange side angle, they would lose the height, the grandeur, and the recognizable shape of the building. These angles provide far less useful information. PCA is simply the algorithm that automatically searches through your data to find this absolute best angle. It identifies the direction that captures the most variation or the most story and projects your data onto it. Each of these mathematically optimized angles is what we call a principal component. The primary reason we desperately need PCA is to combat what we call the curse of dimensionality. This concept describes a frustrating phenomenon. As you add more and more features to a dataset, the data points become increasingly sparse, making it incredibly difficult for models to find any real patterns. Let's look at the bottom left to see this visually. In one dimension, with a single feature, our data points are tightly packed and easy to manage. Moving to two dimensions, the points start to spread across a flat plane, which is still okay. But by the time we scale up to 100 dimensions or 500 dimensions, the data is spread so incomprehensibly thin that it becomes complete chaos. The data is effectively everywhere and nowhere at once, and models just get confused and inaccurate. The takeaway here is that PCA rescues our models from high-dimensional chaos by rotating the data to find the few perspectives that actually matter. To achieve this, PCA follows a specific 5-step process. We have to start with step 1, standardizing and centering our data, which we will dive into next.
So, how does PCA actually process and compress our data? Let's walk through the exact steps. First, the data must be centered. This involves subtracting the mean from every single column so that the entire dataset is centered exactly around 0 on a graph. You can think of this visually. Imagine a sculpture sitting off in the corner of a room. Centering the data is like physically moving that sculpture right into the middle of the room before you take a photograph of it. The object itself hasn't changed its shape. It's just properly positioned to be analyzed. Second, the algorithm needs to find the direction of maximum variance. Variance just refers to how spread out the data points are. PCA looks at the cluster of data and identifies the path where the data is most stretched out. Why? Because this maximum stretch is where the most valuable information lives. Third, we establish our first principal component known as PC1. Look at this graph, where we have two features, weight and height. The data points are spread diagonally because, generally speaking, taller people tend to weigh more. PC1 is exactly that diagonal line drawn through the center that captures this primary spread. As you can see on the next plot, it represents the absolute best angle to show the most variation. Fourth, once we have PC1, PCA finds PC2, the second principal component. If you look at the graph on the bottom left, here is our original first component PC1. The strict mathematical rule for PC2, drawn here in red, is that it must be perpendicular, exactly 90 degrees to PC1. While PC1 captures the main overarching pattern, PC2 is there to capture whatever variance PC1 missed. Finally, in the fifth step, we decide how many of these components we actually want to keep. This is the incredible payoff of PCA. We can take an original data set of 500 incredibly noisy features and compress it down to just 10 clean compact components. By doing this, yes, you might lose a tiny fraction, maybe 5% of the information, but the benefit is staggering. Your resulting model runs 50 times faster, and because you've successfully stripped away all that redundant background noise, the final system is often much more accurate. Now that we understand the process, we can visualize the mechanics of this transformation using a specific example of 1000 people's height and weight.
We can visualize the mechanics of this transformation using a specific example of 1000 people's height and weight. Here we have our original two-dimensional data. The x-axis represents height and the y-axis represents weight. Notice how the dots form a distinct diagonal cluster, because naturally, taller people tend to weigh more. In step 1, our goal is to find the PC1 direction. Because of that strong correlation, the line of maximum spread goes diagonally up and to the right. This is the direction that captures the most variance in our data. Moving to step 2, we project all points onto PC1. Imagine shining a light from the top left and dropping every single data point directly onto that red line. In this new state, each person's height and weight are combined into just one number on the PC1 axis. The result? Two features have been compressed into one number. And we did this without losing the core pattern that tall equals heavy, as you can intuitively see with this simple illustration. But what happens when we have much larger data sets? How do we know how many components to keep? We use what's called a Scree plot, which shows how much variance each PC explains. Look at this bar chart. PC1 captures a massive chunk of the information, PC2 captures a bit less, and the values drop off quickly from there. We look for the elbow of the graph, which in this case is right down here at PC3. This elbow is the point where adding more components gives us diminishing returns. By just keeping the first 3 PCs, the job is effectively done. A key metric to confirm this is the explained variance ratio. In this example, with a massive 500 features, the first few components capture the majority of the data's patterns. When we add up what they explain, PC1, PC2 and PC3 combined explain 85% of all the original information. We've successfully gone from a complex grid of 500 features, put it through PCA compression, and ended up with just 3 numbers while keeping 85% of the story intact. That is the incredible power of dimensionality reduction. Next, we will see how this exact same concept helps massive factories streamline their real-time sensor processing.
The practical utility of PCA is best seen in industrial and consumer applications. Consider Tata Motors' quality control at their Pune plant. Each car is monitored by 847 sensors. Many of these sensors are redundant. For example, engine temperature and coolant temperature move in tandem. Processing 847 separate inputs in real time is just too slow for an assembly line. By applying PCA, Tata Motors compresses those 847 readings into just 12 principal components. These 12 numbers capture 93% of the variation across all those sensors. This allows their defect detection AI to run 40 times faster and improves accuracy by ignoring sensor noise. Similarly, Netflix uses PCA to manage its massive library. Every user has a feature for every movie they might have rated. Calculating recommendations across 15,000 dimensions for 230 million subscribers is mathematically impossible at scale. So Netflix uses PCA to compress these dimensions into roughly 50 principal components. These components represent latent tastes. While the math doesn't name them, they function as categories like action versus drama. This compression allows their recommendation engine to run in real time, which saves an estimated $1 billion annually. Let's walk through the technical implementation. The process begins with simulated manufacturing data, where sensors for engine, electrical, and mechanical systems are highly correlated. The first critical technical step is standardization. PCA is extremely sensitive to the scale of the data. If one sensor is 0 to 100 and another is 0 to 1, the larger numbers will dominate. Standardization transforms all features so they have a mean of 0 and a standard deviation of 1, ensuring a level playing field. Next, we fit a PCA model to analyze the variance. In our simulation, the first 3 components explained over 85% of the variance. After determining the optimal number of components, we project the data down to 3 dimensions. Looking at this 3D scatter plot, even though the data is compressed, the normal and defective cars are remain clearly separated. Finally, we examine the loadings or contributions. PCA automatically discovered physical groupings. PC1 is dominated by engine sensors, PC2 by electrical, and PC3 by mechanical sensors. When testing model performance, the accuracy remains nearly identical between the 10-feature and 3-component versions, but the latter is much more efficient. To master this, consider practical scenarios. In bridge engineering, 200 sensors might measure the same stresses. PC identifies the core movements, like thermal expansion or vibration. When choosing components, look at the cumulative variance and the Scree plot's elbow to ensure you're not discarding important separating information. Always remember, standardize first. If you apply PCA to raw data, the largest numerical ranges will dominate. You must standardize your data first. In summary, PCA takes high-dimensional noisy data, finds the best mathematical angle, and distills it into a few powerful components. This leaves your AI systems faster, cleaner, and far more effective.